We're in Rosen, Discrete Mathematics and its Applications, section 10.5 on Euler and Hamiltonian graphs. This video will cover Euler paths and circuits. And a treatment of any depth of graph theory will almost always encounter the bridges of Konigsberg problem. And the bridges of Konigsberg represent um, some geography that is in Konigsberg, Prussia, now Russia, where we had 4 sections of the land divided divided by this river, and 7 bridges that connected the regions. So we have a little island, 2 banks of the river, and then sort of an isthmus where 2 branches of a river came together. And there was a problem. People wondered if you could follow a path at one of the bridges and then cross every bridge exactly once and get back to your starting point. And the famous mathematician Euler proved that no path exists. It's considered the first theorem proved in graph theory. Let's just try it ourselves real quick. Say we start in B, I cross that bridge, I cross from A over into C, and now I go back to A, then back to B, and then go into D, but now I don't know where to go and I can't get back to B anymore because there's no more bridges back there. Obviously, we could have tried other paths as well. And instead of doing that, let's just write down a model of the Konigsberg bridge problem where our land portions are represented by vertices and our bridges, the 7 of them, are represented by edges. Okay. All right. Now let's talk about Euler circuits and paths. So an Euler circuit in a graph is a simple circuit containing every edge of G. So in our Konigsberg bridge problem, we were seeking an Euler circuit because we wanted to cross every bridge and end back at the starting point, which is what a circuit does. Similarly, an Euler path would be a simple path, one that does not repeat an edge and contains every edge of G, but it does not start and end at the same point. Here we have 3 example graphs, and want to know which one of these has a circuit, which has a path, and which has neither. And I'll let you look at them just a second, but we'll quickly go to the result. You'll see that G1 has an Euler circuit, and I can just trace one of them out here. Here I've started a day and ended a day and went and covered every edge once and only once. It turns out neither G2 or G3 has an Euler circuit, but G3 does have an Euler path. And the trick for this is to note where we have 2 vertices of odd degree. A and B have degree 3, whereas all the rest of them are even degree. And I can trace out an Euler path by going down to the right up to B, and then I can jigsaw back into B. And it turns out that G3 has neither an Euler circuit nor an Euler path. If I start at A and I try to make an Euler circuit, if I go inside, I can't get out back to A, and nor can I tackle all of these remaining edges without picking up my pen. All right. So let's talk about the necessary conditions for Euler circuits and paths. That means if there is an Euler circuit, what must be true about the graph? So if we have an Euler circuit, starts at a vertex A, let's follow it around all the vertices. And the edges that touch these vertices, the first one contributes 1 to the degree of A. And then every time a circuit passes through a vertex, it contributes 2 to that vertice's degree, once to enter the vertex and once to leave the vertex. And then, of course, the circuit terminates where it started, contributing 1 to the degree of A. So I had the starting edge and the ending edge contributing a degree to A. You might have passed through it once or twice. Each of those would contribute 2. So the point is that the degree of A must be even. And indeed, the degree of every vertex must also be even because we entered each one and exited each one that had edges touching it. By similar reasoning, we can see, and we did see earlier, that if you have um, an Euler path, then the initial vertex and the final vertex must have odd degree, but every other vertex will have even degree as above. So those will be the necessary conditions for an Euler path. It turns out that these necessary conditions are also sufficient conditions for there being an Euler circuit in the case of all even, or an Euler path in the case of only 2 odd, or exactly 2 odd. All right, so let's do that proof for Euler circuits. We're going to assume that all of our vertices have even degree. We're going to start our attempted to construction Euler circuit at x0. We'll call that A. And we're going to continue to accumulate edges x0 to x1, x1 to x2, x minus 1 to xn, adding edges until we can no longer add an edge. And it turns out that we must always end such an exercise at the vertex we started at with vertices of even degree. Here we have an example is where I start with A, I add edge AF to my circuit, I add edge, or to my path, add edge FC, add edge CB, just arbitrarily selecting one, then add edge BA, and I'm back at A, and I can't add to the length of my path anymore, and I did generate a circuit. So if it starts at A, it must terminate at A. And since each vertex has an even degree, there must be an even number of edges incident with that vertex. So every time we enter a vertex other than A, we can leave it so the path can only end at A. Now, if all of the edges have been used, we've created an Euler circuit. Yay! Otherwise, we can identify a subgraph here that results from deletion of all those edges we used in the first step. And we'll go to the next slide. Because G was connected at the very beginning, H must have one vertex in common that was deleted, and we can see that that vertex is going to be C. All right, every vertex in H must have even degree. That was the original assumption, and a circuit is going to subtract an even number from any vertex. So beginning with the shared vertex, it will create another path that ends at the same vertex, and we'll splice this in at the original circuit. So we take this new path and we stitch it, actually goes the other direction here. We stitch it into the original right here, DEC. We're stitching into the original path of AFCBA. And we'll do this until all the edges have been used, and this produces an Euler circuit since every edge is included and no edge is used more than once. And you could do a similar type of proof for an Euler path existing when you have 2 vertices of odd degree. So here's our theorem that we've just proved. A connected multigraph with at least 2 vertices has an Euler circuit if and only if each of its vertices has even degree, and an Euler path if and only if it has exactly 2 vertices of odd degree. And now we can answer, using our theorem, the Konigsberg bridge question. Our multigraph representation of it has degree 5 for landmass A, degree 3 for all other land masses, and we can see that we have more than 2 vertices of odd degree, so we will not have an Euler path nor an Euler circuit. And that is our discussion of Euler paths and circuits in graphs.